Hi all, welcome. Our speaker today is going to be Professor Negar Elhami-Khorasani. I'm sorry, if I'm wrong. She is Associate Professor, Civil Structural Environmental Engineering, University of Buffalo. Her primary areas of research are structural engineering, resilience of communities under extreme hazards, and characterization of cascading multi-hazard events. She's the co-chair of ASE SEI Fire Protection Committee, co-chair of the CIONI Resilience Committee, and serves on the board of directors of Applied Technology Council. She is associate editor of the Fire Technology Journal, and she has done a lot of other things, won a lot of awards, which I'm not going to get into detail now. So thank you very much, Professor Elhami-Khorasani, for this. The title of the talk is Structural Damage from Wildfires in Wildland-Urban Interface Communities. Thank you. It's all yours.
Thank you. Let me share my screen. See. Yeah, this is good. You can see it, right? I assume. Okay, just gonna move on. So good morning, all. Thank you, Dr. Sranani, for the introduction. It's a pleasure for me to present this group today, and I thank you for the invitation. So I'll be presenting parts of our work on structural damage from wildfires in wildland-urban interface communities. And I want to start by pointing out that not all fires are bad. We need wildfires for a healthy ecosystem. But the problem arises when these fires become intense, they spread fast, and they reach communities, and they lead to destruction. So I'm going to start with a video. This is a drone footage of the Lahaina fire on Maui that happened last summer, less than a year ago, and you probably remember this from the news. This is officially now the deadliest wildfire event in the US in the past 100 years. It had over 100 lives basically lost during this event. So I'm going to come back to this towards the second half of this talk as we simulated the event and we're trying to understand what happened. But you see the level of destruction in a community. It's just more than 2,200, more than 2,000, let's say, structures burned down in the area. So in terms of motivation, in the past few years and looking back at historic data, we see that the frequency of large and severe and destructive wildfires has been increasing. And part of that is because of climate change. And part of it is because of urbanization. We are building these wildland-urban interface communities that are basically could be subject to these wildfire events. So these are the main drivers of the problem, and they're not expected to improve in the near future. So the idea for our work is to come up with risk assessment methodologies for communities for the wildfire hazard. Now, existing wildfire risk assessment procedures primarily rely on exposure and historical data to prioritize these communities without really explicitly simulating the community response and looking at the vulnerabilities inside the communities. And that's what we have been working on. So the philosophy behind our work is we're following this performance-based design philosophy that we are adopting from earthquake engineering community. So performance-based design for earthquake engineering has been very well established. It has been also adopted to other hazards such as performance-based design for wind. Now, if you're familiar with it, these boxes probably you see the mapping between earthquake, wind, and now wildfire. So what we're looking at basically when we want to perform an assessment, we have to start with a domain. We look at our domain. This domain, yes, there's a community, but there's also the wildland area around the community. We have to come up with boundaries. Then we have the hazard analysis, basically inside the wildland. Where could we have ignitions? And once we have an ignition, then the fire starts. If it goes out uncontrolled, then it's going to spread inside the community. So we want to be able to, and there are tools out there that can simulate fire spread inside wildland, but then that fire line can reach a community. So then we want to take over and look at fire spread inside the community. And then once we model that, then we can quantify damage. And once we know the damage, we can perform loss analysis. And loss analysis, it can go beyond just economic losses. It can be direct, indirect, short-term, long-term losses, social losses, and so on. So the one important aspect here is that in each box, the idea is that we look at the uncertainties, and then you have this uncertainty propagation from one box to the other, to the next one. So it can capture basically the randomness in the process. Today, I'll be focusing on urban fire model. So the tool that we've been working on in order to capture fire spread inside communities and understand what happens in these communities, and then start quantifying damage in these communities. So basically what overall we are after is we want to quantify. We are after this quantitative assessment of vulnerabilities and the drivers of loss in communities, and we can adjust. Once we know that, once we understand that, then we can adjust and recommend guidelines to reduce losses to an acceptable or tolerable thresholds. For example, we know that increased distance between buildings, once we build them further apart, then there's less likelihood of fire spread between, if a structure is on fire, the nearby structure where there's a distance between them, well, there's less likelihood of fire spread. But should that distance be 30 feet, 100 feet? How does that influence the fire spread in quantitative way? We don't know all the details, and that's what this research is after. And it's basically important to evaluate the effect of different mitigation actions in these communities. We know fire resilient construction would help. We know defensible spaces. So basically, you've got a house, you've got vegetation around your structure, you need to trim that vegetation to, again, cut the path for the fire to spread to your house. So the idea is that single activity, well, it could help, but it may not be enough. So what's the effect of a combination of them? What's the basically priority? Which one would be more effective? So towards the end of the presentation, I'll show you one example. This is right now, we've got to the point that we're looking into this, but this is right now in progress. So I'll show you one example. But before we could do this, we had to come up with a way to capture the spatial and temporal behavior of wildfire inside these wildland-urban interface communities. And that's what most of the presentation will focus on. So let's talk about a little bit of background on how, like, it's just the physics of the problem in terms of how the fire actually spreads between structures, as well as from wildland to structures. So fire mechanism, the spread mechanism is similar in the wildland as well as inside a community. So direct flame contact is when you have the flame moving and touching the surface of the building that's causing the fire. Basically, you've got a lawn, you've got trees, you've got vegetation, they catch on fire, then you've got that direct line. If you have that path, then the structure catches on fire from the flame. Got radiation. Radiation is when the heat moves through space as energy waves. So again, back to physics 101. Convection is the transfer of heat through hot masses of air. And then we have this other mode of fire spread, which is a major mode. It's called fire spotting. So these are basically burning embers that they detach from both houses as well as trees and vegetation, and they're transported over large distances, and they've been identified as one of the significant causes of fire spread. These embers can arrive from the wildland and get into the community, or from a house to another house inside the community. And the process is basically involve the fire brand. They generate, then they get transported, and then they land. And if there's enough of them, these are hot, basically, pieces, and they're still burning. So these pieces, once they land, if there's enough of them, they can cause ignition where they land. If there's a fuel, there's something combustible, and this process is influenced by wind. So when I say this is a major fire spread mode, is in events we've seen that the fire is burning in the wildland, it gets into a highway, a major highway can be, I don't know, 8-lane highway. And then because of this fire spotting, it's a windy day, so the embers get transported over the highway, and then there's a new fire line developed, and then the fire continues. So the fire can jump. So what we have been working on is developing this tool, what we call it SWIFT, a streamlined wildland-urban interface fire tracing, which captures the fire spread inside communities. There are currently 3 types of fuels in the model: structures, vegetation, and non-combustible. And by non-combustible, I mean basically roadways, anything that doesn't burn. If you've got a pond in the middle of a park, as well as the type of structures, if you've got a reinforced concrete structure, that's a non-combustible, basically fuel for this code. And then we have radiation and fire spotting modeled in the code. We also have a built-in mechanism in the code that if you have part of a house on fire, then the fire is going to, these are typically, timber frames construction in wildland-urban interface communities. So the fire spreads within the house over time. We do have evolution of the fire. So there is basically the fire first starts, it heats up, then it's fully developed. When it is fully developed, then you get radiation spotting. It develops this energy and develops the embers, causes fire spread. And it basically, we also have vegetation. So the vegetations either burn or then once they're burned, then there's no fire spotting coming from vegetation. And it tracks the amount of energy and these embers over space and time. And once they reach the thresholds at a given location, we've got ignition and again, a new fire and continues. One thing I want to point out is the resolution. So when we track fires in the wildland, we typically go on, kilometer scale. The fire can burn over days. With communities, we want to be able to capture what happens in a house. We want to capture distance between the houses if there's a roadway. So we can't really work with kilometer scale. So we need to go down to meters. And then we also want to see exactly like what happens again inside the community, how the fire progresses. So we're again working with minutes in these simulations. And then the philosophy behind this, the way that we're working on this without getting into too much detail, is we can't really follow the physics of every piece of this problem. And when I say every piece, think of fire spotting, the generation, the transport, landing, capturing all those from a physics-based perspective, it becomes quite complex. And going back to the beginning and motivation of this talk, I talked about risk assessment, and we want to capture uncertainties, right? And we want to run these models many times. So they need to be computationally, to some extent, efficient. So that's why we're combining theory and physics. Radiation is, driven. The equations of physics is built in the model. Where there are pieces of this in the background where they're data-driven models based on experiments, including, for example, the fire spotting. But they're probabilistic models. So it means that we actually try to capture uncertainties in all different aspects of this fire spread so that we can look at different type of response that we could get inside a community. In terms of the input to the model, we need definitely the building footprints. And with the building footprints, it then gets so here you see a satellite image and then an image that basically shows what goes in as an input to the model. We've got the vegetation, and anything gray here is basically non-combustible. You've got, again, roadways and so on. So I've been focusing so far on what happens in the community, and that's our research. So that's our contribution. But if we want to do a full risk assessment procedure, we need to also connect to the other boxes that I mentioned, which is hazard and the wildfire in the wildland. So we need to be able to so somebody is modeling fire in the wildland, and then we need to get that fire line and transfer it to the community. So we have worked on this seamless simulation from wildland to urban areas, creating like developing methodologies. And we've been looking at it from different aspects. Number one, the model is quite efficient. Runs relatively compared to when I say fast, it's not necessarily seconds, but relatively to these events in real time when a fire spreads. We've come to the conclusion that we can actually use the model for real time. Oh, there's a fire is approaching the community. Can we run it? It goes faster than real time and gives us an idea where the fire could go in terms of coming up with strategies. We see possibility for that. So what the first idea was, okay, let's connect to a fire line in the wildland that comes from radar observations. These are weather radar observations. Collaborators have been working on it. So takes the fire line in the wildland in real time and then transfer it to the community and simulate the fire. The second idea, again, for prediction purposes, for risk assessment, we've been connecting to a simulation tool for wildfires called weather research forecasting. So that's a WRF, it's a weather model, and it has a fire module, so it's WRF fire. And this is a coupled wildfire it's a coupled wildland fire behavior and atmospheric model. So these fires, you might have heard about this, that they generate their own weather. So once you've got a fire, it's burning, creates this heat that feeds into the atmosphere, and that changes the pattern, the wind pattern. And then, so there's that coupling effect that fire captures. So we've been working again with collaborators and connecting with Warfire for risk assessment. And then what happens now? So in the wildland, whatever it has to come from another source, the fire line. And then the community, that's us, that's SWIFT, that's fully in control. And then we've introduced this zone, transition zone, that the fire's still spreading in the wildland, so we are not in full control. But what we are after is that I mentioned these embers, this fire spotting, that could cause ignition. So the transition is where you've got a few kilometers, it's close to the community, these embers could fly and get into the community, so we want to be able to capture that. So in the transition zone, while the fire line is moving from different source, we actually activate our tool, the SWIFT model, the fire spotting module, to generate these embers and then transport them and see if they land in the community and if there's enough of them to cause ignition in the community. So we want to be able to capture those. So I am going to move into case studies now. And I have a few case studies. I'll first start with these two. The first one is Campfire, happened in 2018. And this event, you can see the amount of destruction, more than 18,000, almost 19,000 buildings destroyed and damaged. The Marshall Fire, the second case study, not that many, it's like less number of damaged structures, but I want to point out that it happened in December 2021 and it happened in Colorado. So Colorado is familiar with fires, but this happened right before Christmas. So what used to be a fire season maybe doesn't apply necessarily anymore. And the day after this event actually snowed. So the two case studies, they're different in the sense that one, we connected SWIFT to, again, weather radar data from the wildland. They do not come at fine resolution. You're going to see in the simulation that it kind of like the fire jumps in the wildland. It's just amount of data that comes from real measurements. And then SWIFT takes over inside the community. With the second case, we actually connected with Warfire, so it's a different application. So let's go through these two case studies. So the first one, this is gonna keep going, so it's okay if the first time don't see all the details. So what's happening is you've got an ignition. Anything that's dark green, it means like it's a burned vegetation. This is a zoom. This is Community of Paradise. This box, you see it here on the right, the zoomed in version, and anything that's red ish, purplish, that's the structure, different phases, like when it's burned. And these are weather radar data again coming in, and then from the yellow boundary crosses, that's the transition zone. And then we follow, this is Swift simulating fire spread inside the community. And you can see that it's a pretty dense, like you've got many structures, but you can also see how dense of vegetation we've got. We've got structures and vegetation going on quite dense in the area. So once we did this, okay, how did we do in terms of prediction? This is not calibrated, it's just the output of the model. And we're looking at this and say, okay, we need to have some evidence of, validating this model. So NIST, National Institute of Standard Technology, had a study. They went to the area, collected data after the event, and tried to put together as much information as possible in terms of what happened. So it's not a complete picture from the report, but it has enough details for us to look at how our model is doing. So between 7:45 and 8:30 a.m. during that day, they're reporting that they were probably fires where you see there a circle or a triangle, any red point basically could have been a fire at that location. And we're looking at our model, this non-calibrated version. Well, it's kind of a little bit behind here, but again, this is just one scenario. We're not running this 1,000 cases. It's okay. It's a little bit behind. Fine. Now 9 a.m. This is the model again. It's catching up. It's the north. It's capturing the fire spread, and here it's also moving faster. This is 10 a.m. This is 10 a.m. NIST. The model might be a little bit going faster now, at least in this area. Here we don't, NIST is not reporting any ignition. Maybe they missed it, we don't know. But overall, again, considering the uncertainty in the event, this seems like we were able to capture the way that the fire moved inside the community through the model. So then we moved on to the next event, 2021 Marshall Fire. And I want to point out again, in terms of scale, the other event here, you could tell it was something in the order of 800 square kilometers. This is a smaller scale for the simulation in terms of area coverage. And this is so the fire happened somewhere around here. There were 2 ignitions, and then there's Louisville and Superior. These 2 communities got impacted. And there's a Highway 36. I'm going to mention this in the simulation, so keep an eye on it. And this is how, so the yellow is where the community Swift is going to be activated, and the blue is the transition domain where we are going to generate fire spotting, but we won't be responsible necessarily for the fire line movement of the fire line. So, okay, let's look at this. So this is Wharf now, Wharf Fire, simulating the fire. 2 ignitions, the fire moves, gets to Highway 36, goes over, and now it's, so take a look at this. Here it's showing gray, which means for us non-combustible. So when we started simulating this event, we are looking at the structures, and we are looking at this area. There's a highway, there are commercial structures, there are a number of commercial structures located in this area. And when I say commercial, think of, for example, there's a Walmart. So it means you've got these industrial type buildings, and then you've got these large parking lots. So they're different than these timber frame construction again. So the way that we build is different. So we remove those structures do not count as a regular, basically timber frame structure that we set the ignition thresholds for in the model. So we removed these structures out of the model. They did not deserve basically to be there. So what happened was, I'm gonna rerun. So the fire actually goes around and then enters the community from the north side. So we also ran, I'm not showing this here, but out of curiosity, we also kept the buildings. And in that case, the fire went through right here, and then it was way faster. So we're like, okay, let's look at again what happened in reality and try to figure out actually if we got it right, or are we making this up? So how is this right? Is this actually realistic, or do we need to keep these buildings? What's actually more realistic? So we had at that point seen the NIST study, and we were wondering if there's anything similar available for Marshall Fire. It was not, but there was a local reporter in the area, lived here, who collected hundreds of videos from citizens, like local citizens, and put together on the web basically timeline of the fire. But it wasn't just the fire. He basically collected any video that had the smoke, people evacuating. So what happened was that my student actually went through those videos, and about 100 of those actually had active fire, where you can see the fire burning. And then he also validated the location, so the timestamp and the location. He went to basically Google Street View and said, okay, here's what I see in the camera, here's the location, is this correct, is this not? There were some fixes that had to be done. So we're looking at this, and we say at 3 p.m., Wildfire is saying that, okay, we're just crossing Highway 36. Whereas based on evidence of on the ground observation, these triangles, this like bluish, 12 to 2 p.m., we see the fire actually in this area. So I mentioned error, uncertainty propagation. Now I'm going to mention error propagation. So Wildfire, actually, I'm not blaming Wildfire in this case, but there is an error right now we see in Wildfire that we know potentially why the fire could be. So Wildfire doesn't have fire spotting, and we're working on our collaborators. They're working on implementing fire spotting. So the fire would move slower in some cases where there is potential, there's like wind and there's potential for fire spotting. So knowing that, okay, but how about Swift? How is the Swift doing? So we did get, so even in reality, we see that the fire, so you see these structures didn't get damaged. Actually, fire went around, entered the community from this side, and then continued burning along that way. So when we look at our simulation and the pattern of the fire going around, coming from the north versus, again, observation, we see, okay, that makes sense. So the model is working. Last case study in terms of validation. Lahaina, I'm going to go back to where we started in this presentation. So about, again, more than 2,000 buildings destroyed. You saw the footage of the destruction. Here's also an image. The fire happened, I think, on a Wednesday morning, if I recall correctly. And then the result I'm going to show you, we've improved this model since, but I purposefully kept the same simulation that the first basically pass. We decided right after the event to let's simulate this. And by the Tuesday after, so less than a week after the event, we got these results. So how did we approach this? We said, okay, here's the area domain of our study. It's actually a pretty small domain compared to the other cases I showed you. We don't know exactly where the fire started, still under investigation, but there's an overpass here. The region where the fire started, we know it's somewhere here. So we put the fire. You're going to see in the simulation, the fire basically enters the community. This is historic town Lahaina. And here there is a front street where people trying to evacuate. So what I'm going to show you on the next slide is around, we know, again, we have video footages of people at 5-ish p.m. local time, 5:30. There's fire burning in historic town. And then around 7 p.m., we see people in front street where they can't evacuate. The fire is moving fast. There's like traffic gridlock. So people start jumping in the water to save themselves. And that's happening around 7 p.m. So I'm going to come back to that, 5:30 and 7. So the fire happens so close to the community. You know how I've been talking about, okay, we need to connect to another tool to track the fire in the wildland. We didn't need to connect to any tool in the sense that, well, here it's just so close to the community. Swift is going to model this, fine. But we needed input for the wind. Our first idea was to grab the wind from actual measurements from a weather station nearby. But it turned out that there was no weather station near town of Lahaina, and therefore that idea didn't work. So then we went back to our collaborators, whether in WRF, we can simulate detailed wind, and this is actually an LES activated version where we see the turbulence. So you see how all these arrows basically, it was a windy day and it was high wind event. And not only that, but also basically the wind simulation shows that there was a hydraulic jump. So what it means there's the wind is coming down slope and then it detaches from the surface. And because of that, it causes turbulence. And because of that turbulence, without going again into too much detail, what's happening is that because of turbulence, you get fire to spread both north and south, and it makes it hard for people to evacuate because the fire is spreading in all directions. This is the building footprint input. Because we were doing it so quickly at the time, it's just right after the event, we got building footprints from this Microsoft data set, which is open source. But then we realized, my student realized that, okay, there's so many missing points for Lahaina. So he used just satellite images to add all the missing footprints at the time. So again, this is going back to last August. So this is the simulation result. The fire will start here around 3:30. Again, don't know exactly. We know that's around the time that started. Wait until 5:30. So this is 5-ish, and we see that this is historic town. It's burning. Okay. And by 7, we are hoping to see the fire here. Yes, that's where people were started to jump in the fire in the water. And the fire, again, because I mentioned it was the wind condition, it's moving both towards south as well as north, and spreading in all directions. So another validation point we were able to get, so this is just a contour of what was shown in the previous slide. So green is before 3:30, and then the fire yellow, and it gets reddish, so it's expanding, and then the gray is 8:30. We do have one satellite image showing 10:25. There's an active fire here in the north, and there's an active fire here in the south. These buildings that are, again, red, purplish, they're burning, and these buildings here, they're burning. So seems like we got this. Again, at the time, we didn't even have detailed data, and we've been working on. So this led to another collaboration with the University of Hawaii, a rapid NSF rapid grant. So we are now working on going into more detail of trying to find out some of the vulnerabilities in the town and verifying this model further. Okay, I've got 10 more minutes, and now I'm going to slightly shift gears. And at this point, I'm going to assume that the model is validated, or we have some confidence, basically, in terms of it's not out of luck that we are getting a reasonable performance in the model. But we looked at California, Colorado, Lahaina, no calibration. Seems like logic, physics is working. So these 2 case studies, they're here to, I'm going to go back to that risk assessment idea and how now we can start using the model to basically guide some decisions. I'm going to go step by step. So with these 2 cases, I'm not going to get to decisions yet, but you're going to see some probabilistic aspects here. So the left one is Wichin-Cojito fire back in 2007. It happened in California. Second one is Tubbs fire in California, happened in 2017. Both of them, we're looking only at the community. So at this stage, just focusing on the community. These are 2 different community, like they have different characteristics, and you're going to see that in the simulation results. Here on the left, you've got these buildings that they're the distance between structures is not too dense, whereas here in Fountain Grove, the second case, we see the fire spread, the fire spotting causes a fire line here and then another fire line. And then the structures are so close that it's actually radiation taking over and spreading the fire. Here, this is already over. Here, you still have fire spotting causing the fire to spread, but the buildings are further apart. So it's harder for radiation to cause ignition. So when we put them side by side, then we're going to go into the detail and like try to get more result out of the model. So on the first case, when I said the structures are further apart, we're looking at the cause of ignition. This is fire spotting, and red is radiation. You see more ignitions due to fire spotting. And it makes sense, again, considering the distance. So the way it was built, radiation didn't contribute. And by the way, I'm going to come back to this, but they were able to suppress the fire in this case. Here, the whole thing, this area completely burned down. They weren't able to suppress. It was an intense fire. And we are looking at this. It started with fire spotting, the black line. So we saw a fire line jumping, another fire line jumping. But then after we had those ignitions, then we had radiation, the red line taking over because the structures were built close to each other. So let's say now we have these two areas. They want to do some sort of assessment. So we run thousands of cases. What do we get out of, and we didn't know about these events. What would we get out of those 1,000 cases? Varying the inputs. This is not a specific now scenario. We are looking at a risk assessment, varying all like different potential scenarios. So with the first case, that was the one that they managed to suppress, and fire spotting was the primary mode of fire spread. This is a result of thousands of simulation, and we have here the cumulative distribution function for the total number of ignitions over time. So we see here in 30 minutes, 60 minutes, nothing really is going on. It's like sitting at 0. And then if I move forward all the way to 180 minutes, we have the median is around 73 structures. In reality, 90 structures burned during that event. There is a range from 40 to 180. Looking at this, well, aside from the fact that reality of that event versus the median from these thousands of simulations, they're close, great. But looking at this, we see, okay, the fire, it took more than an hour for it to really get momentum. And that provides opportunity for suppression. Now, if I go to the second case, where radiation also contributed, I'm looking at 30 minutes. Right there, you have a whole range, and you can we had scenarios which led to large number of houses on fire in only 30 minutes. So by the time we get to 120 minutes, we have a median of about 160 structures on fire. And here it shows you that the way that this community looking at different scenarios where it looks like the risk is higher, and there is potential for fast fire spread quickly, which makes it hard to stop the fire. Okay, so now let's look at, I'm going to go back to, again, the objective of the study. And I said we want to quantify some of the things that we know they would work. We know if we build further apart, it would help. We know if we cut vegetation, it would help. And we know that if we build better, what we call structure hardening. So I'm going to quickly mention that you've got a house, the detailing of the house, the type of the roof, the type of the siding. If you've got a fence that's out of wood that is connected to your house, if it catches on fire, it provides a direct path of the fire to your house. If you've got a deck, timber, connected. So all of these details would matter. And if you build in a way that stops or provide a barrier for the fire to spread, then what we call structure hardening. You don't have to build out a concrete or steel. It's about the detailing. If all you need to do, for example, is to add a screen on the vents to prevent these embers that I mentioned to enter inside the house and create an ignition inside the house. So it's called structure hardening. And there's this NIST document that basically categorizes these communities and say if you build 6 to 30 feet, it's pretty dense, 30 to 100 feet, medium density, 100 plus is low density. So we've got all of this. This is where the research is in progress, and we are going through different scenarios, looking at effective different measures. I have one example for you, and considering the time, I'm just going to show you this one example. So we're going to look at two communities. The first community has a structure like both of them have the same structure separation distance. They have structures that are built 30 feet apart. The wind speed, let's keep it the same. It's a windy case, which is typical. Again, this is a typical, could be a destructive event, 45 miles per hour. Vegetation cover, same 30%. And then one community is an existing community, doesn't do anything in terms of retrofitting. So it's as built and it's pretty vulnerable. And then the other community, yes, there's a policy aspect. Where does the money come from? But they know that they have a risk. So they get together and they figure that they need to do structure hardening, and they implement that. And they retrofit the structures, 70%. Fine. How does, let's say, same fire event, how do they respond? And these are idealized scenarios. So the left one, again, follow the red. The green is vegetation. It's okay if they burn. This is already burned down. Whereas here you see the fire spreading still across the community. So the change in fire spread rate with structure hardening in these two communities, there's a 40% reduction. And just that, so we don't have suppression built in this model, but that could be enough. This depends on, we have to kind of work with the community, the resources, the fire chief, fire departments, and emergency response offices. But a 40% reduction in fire spread could imply that now they have an opportunity to suppress the fire and prevent it from further spreading inside the community. So in summary, we have developed a model to capture fire spread inside WUI communities, and the model accounts for structural fuel. This is something that didn't exist when we started this work. There are a couple of research groups now working on the problem. We wanted to make sure that we could enable a seamless simulation of fire across wildland and these WUI areas, so that we have this, what we call offline coupling of SWIFT with other models. And then we have come to the conclusion at this point, considering the capabilities of the model, that we can identify vulnerable areas in WUI communities, we can guide mitigation actions in WUI communities, and we can also use the model to guide, once you know how your community could respond, you can also use it for emergency response management and also decision-making during an event. And with that, I want to thank first my team. This, it cannot happen without great students. And I think I saw Dr. Masoud Waziri on the call. I hope he's still here. And thank you for all his efforts on the call, on this research. And current PhD candidate, Fernando, has been moving the research forward. Very thankful to him and all the collaborators, as well as the funding agencies. And with that, I've got 1 minute. I'll stop and I'll be happy to answer questions.